Hello general chemistry students. This is the fourth video in week 11, and in this video we're going to be exploring the collision theory. And then we're also going to be looking at how the Arrhenius equation and the collision theory are related. Alright, so by the end of this video you'll be able to explain how or describe, I guess, the collision theory of kinetics and how it's related to the Arrhenius equation. And so really what we're getting at is we need to be able to explain on a molecular level how kinetic energy and reactivity are related to each other. All right, so we're going to talk about the molecular interpretation of the reactant nature, temperature, and concentration. All right, so let's talk about the collision theory of kinetics. And when I think about this theory, what I'm thinking about is about a pool table, all right, where you hit balls on the pool table so that they collide with one another so that you can get the ball into the hole, right? So that's the idea of pool. And really collision theory is just like this. So instead of billiard balls, we're working with molecules and they are colliding with each other. And when they collide with each other, if they have enough energy, then they will form product. And so interestingly, there are about 1 billion collisions of molecules per second. So on average, about 1 billion collisions per second. Many of those do not form product. All right. Once a molecule collides, they can react together or not, depending on two things. Does the collision have enough energy to break bonds and hold reactant molecules together? All right, so we need to break those bonds of the reactant molecules. So that's the first thing. The second thing is, when the reacting molecules collide, are they in the proper orientation for bonds to form? Okay, so is there enough energy? Are they in the right orientation? So the collision theory really comes down to those two things. If two molecules collide, they must have the appropriate energy and they must be in the right orientation. This is why many collisions do not result in reactions. Okay, so here we have all our molecules, they're floating around, and there's lots of collisions that are happening. So for a collision to overcome the energy barrier, so remember that energy barrier is our activation energy, they must have sufficient kinetic energy. Okay, so how do we provide kinetic energy? Well, we could provide kinetic energy by temperature. We learned that with the Arrhenius equation. So that'll help. And they must have enough kinetic energy so that we can form that transition state or the activated complex. And so we can see from this diagram that there's lots of collisions happening, but the ones that you see in yellow are the ones that are leading to product. Those are the ones that have both the right amount of energy for collision and the right orientation. Okay, so let's look at this reaction. So we have two molecules of NaCl. They're going to collide with each other to produce two NO molecules and a chlorine molecule. So think about what has to happen for this reaction to happen. So here we're assuming that let's assume that all the collisions have the same amount of energy and it's sufficient energy in order to surmount that energy barrier. All right, so then the other thing we have to think about is the orientation. Okay, so what do we want to happen? Well, we want those chlorine molecules to form, and we want this nitrogen-chlorine bond to break. All right, so we want to break this bond, and we want to form that chlorine bond. Okay, so what kind of orientation do we need? So if we look at the top one, which I'm calling ineffective collision, we have the collision between the oxygen atoms. Okay, so that's not going to get us to a chlorine molecule. So that's ineffective. It doesn't have the right orientation. And then the next one, I have a collision between chlorine and oxygen. Again, that's not going to get us to our chlorine molecule. But the effective collision is the collision between those two chlorine atoms. All right, so they're going to collide. They can form a bond, and then the nitrogen-chlorine bond can break. All right, they're in the right orientation. So provided they have the right energy, they're certainly in the right orientation in order to react. All right, so collisions in which these two conditions are met are what's called effective collisions. Effective collisions are the ones that make product. So the higher the frequency of effective collisions, the faster the rate. Okay? So the more effective collisions there are, the faster the rate there is. All right, so that should make sense. All right, so if two molecules have an effective energy, then they form an activated complex. Okay, so let's go back to what we talked about. So we have two molecules, they come and collide. All right, they have enough energy. They're in the right orientation. That's called an effective collision. When they do that, they form the activated complex. All right, they form the activated complex, which you may know also as the transition state. So that effective collision is forming that activated complex. Okay, so now let's bring in the Arrhenius equation again. So we talked about the frequency factor in the Arrhenius equation, and so we're going to break down that frequency factor to what exactly does it mean. And so it's going to be broken down into two terms that says whether or not a collision will be effective. All right, so our two terms for our frequency factor is this P and Z. Okay, so we're breaking down that frequency factor even more to align with our collision theory. Okay, so the collision frequency is the number of collisions that happen per second. Right, so the number of collisions that happen per second. All right, I'll do this. And the more collisions per second there are, the more collisions can be effective that lead to product formation. All right, so pretty simple. More collisions, more product. Okay, and the other part of the puzzle here is that orientation factor. So the orientation factor really is a statistical term that relates the frequency factor to the collision frequency. Okay, so for most reactions, P is less than 1. All right, that makes sense because it's a statistical term. And reactions that involve atoms colliding, the more spherical they are, the closer to 1 they are. All right, so that's the orientation factor. All right, and so the orientation factor really has to do with the proper orientation of those atoms. So we talked about the reaction of NaCl to form that chlorine bond. It had to have that right orientation or it wasn't going to work. All right, so reactions where the symmetry results in multiple orientations, okay, so like our example with our NaCl, P is going to be less than 1, right? So not every collision is going to have the right orientation. Okay, so let's dig deep into the factors that affect rate. So we're going to talk about a molecular interpretation. So we did talk about this when we talked about rates of reactions, but we didn't talk about it really in the molecular way. So I told you there's 3. The first one is the reactant nature. Okay, so what do I mean by that? I'm talking about solutions. I'm talking about gases. I'm talking about liquids. Okay, so we can say that reactions generally occur faster in solution. All right, they occur faster in solution than in pure substances. Okay, and so mixing helps. The particles are separated because they're in solution, making more effective collisions. The forming of solutions breaks bonds that need to be broken. So there's lots of reasons why reactions tend to occur faster in solution. All right, so some reactions occur at different rates, either have higher initial potential energies or they have lower activation energies. So remember the interplay here, right? So higher initial potential energies of those reactants, or maybe a lower activation energy. Okay, so let's think about this. So the reaction of methane and chlorine to form CH3Cl is 12 times faster than the deuterated form, so CD4. So deuterated is a proton that has one extra neutron. So it is an isotope of hydrogen. All right, so it's 12 times faster than doing the deuterated form. And the reason that is because the CH bond is weaker. Okay, so this is an example of higher initial potential energy. Okay. Another example is the fluorination or chlorination of methane. All right, so X is either a fluorine or a chlorine. If we look at the activation for fluorine, it's 5 kilojoules per mole, but for chlorine, it's 17 kilojoules per mole. So the reaction is going to be much faster for fluorine with the lower activation energy than for chlorine that has the higher activation energy. Okay? All right, and we also learned that the rate is going to be affected by temperature. And we know that, we've been talking about this from the very beginning of general chemistry, that when we increase temperature, we increase kinetic energy. We increase kinetic energy, we are increasing the number of collisions, which means we're increasing the number of possibilities at where the molecule have enough energy to overcome the activation barrier. All right, so increasing temperature, really, really important here. Increasing that temperature will increase the number of molecules with enough kinetic energy to overcome the activation energy. Quite simply, raising the temperature increases the rate. All right, another thing that's going to affect the rate is concentration, with the exception of zero order reactions. Okay, so typically reaction rate is going to increase when you increase the concentration or a partial pressure of a reactant. Not true for zero order reactions, so that's different. And the reason that is because more molecules leads to more collisions. And more collisions, there's more possibilities of having enough energy to make product. All right, so that's the end of this fourth video where we talked about the collision theory of kinetics and applied that to the Arrhenius equation.